Section 3.1, Vector-Valued Functions. We spent a long time in Chapter 2 learning about vectors, all for this in mind, to work with vector-valued functions so that we can do calculus on these vector functions. So let's take a look. A vector-valued function is a function that takes in an independent parameter. We often use t, and it produces position vectors. Remember, position vectors start at the origin and point to some point in space. Each one of these position vectors has a terminal point, and the collection of all of those terminal points is what makes up a curve in 3 space. Now, when we look at our function, r of t, this is the vector function. I know it's a vector because there's the little arrow on top of the r. I can see that I'm writing that as a position vector, but then I can also see, using the standard unit vector notation, that this vector function is actually made up of 3 separate component functions. These component functions are multiplied to the standard unit vectors I hat, j hat, or k hat. They are not vectors themselves. F, G, H, those are actually scalar functions, just like the functions that we used in Calc 1. I made a little illustration here to show you how vector functions produce curves. They start with something like this turquoise vector, and for each value of t, that vector points to a different place in space. And if we imagine a terminal point at the tip of that vector, and then we imagine how that terminal point is tracing out in space, we can see that this is generating a curve that's really unique. In Calc 1 and previous math classes, we weren't allowed to create functions that looked like this. One, because we didn't have the tools to do it, but also because our rules said that functions can't twist back on themselves. They can't cross through themselves. But with a vector function, that's not a problem. So this really opens the door for us to work with much different curves than we would if we didn't use vectors. Evaluating vector functions is just like evaluating functions from before. In fact, we even use the same notation. So if I'm looking at a function r of t and I want to evaluate it at t equals 0, I'll write r parentheses 0. Or if I wanted t at pi over 2, I could plug pi over 2 into the parentheses, or 2 pi over 3. So I could evaluate this function at each one of these different t parameters simply by replacing t in the definition of the function with the value that's in the parentheses. So r at 0 would mean replace t with 0. Well, 4 times cosine at 0 is 4. So we have 4 I hat. And then 3 times sine at 0 is 0, because sine is 0 at 0. So the vector r, with t equals 0 plugged into it, creates the vector 4 I hat. Moving on to r at pi over 2. This time I'll replace t with pi over 2 instead of 0. And if we have our trig functions memorized, then we can quickly evaluate this. If not, pull out your calculator. 4 times cosine at pi over 2. Well, cosine at pi over 2 is 0, so the I hat component is 0. 3 times sine at pi over 2. Sine at pi over 2 is 1, so that would be 3, and that's in the j hat direction. All right, we have one more to do, and that's at 2 pi over 3. Now this one, I want to remind you of the corresponding angles that we have in quadrants 1 and 2. So 2 pi over 3 is actually over here in quadrant 2. But we can use what's called a corresponding angle, which would be pi over 3, from quadrant 1 to answer our questions. The only difference we would have to do is modify by a positive or a negative multiple. There's this little shortcut that helps me remember how to use the negatives. All students take calculus. A in quadrant 1 means all of my trig functions are positive. S in quadrant 2 says only sine is positive, cosine and the other trig functions would be negative. Tangent is positive in quadrant 3, but sine and cosine are both negative. And then cosine is positive in quadrant 4, but sine and tangent are negative. So using this idea, I'm going to use pi over 3 in quadrant 1 to answer questions about sine and cosine at 2 pi over 3 in quadrant 2. For example, cosine at 2 pi over 3 can be replaced with cosine at pi over 3 as long as I take into account that cosine is negative in quadrant 2. And sine at 2 pi over 3 is equal to sine at pi over 3, because the only difference in quadrant 1 and quadrant 2 is whether or not sine is positive or negative, and they're positive there, so I can replace those straight away. So r, our vector function with 2 pi over 3 plugged into it, would look a lot like if I did pi over 3 as long as I adjusted my cosine by a negative. So let's evaluate these two. Cosine at pi over 3 is 1/2, so I have negative 1/2 here. Sine at pi over 3 is root 3 over 2. So evaluating the vector function r at 2 pi over 3, we have 4 times negative 1/2. That gives us negative 2 in the I hat direction. And then 3 times root 3 over 2 for the j direction. Whoops. And I've generated a little graph here that plots each of those vectors that we just found in white. Let's take a moment to see if we can identify which vectors are which on this graph. The orange curve, the ellipse that you see on the screen, that's the entire set of points that make up the vector function r of t. But the 3 vectors we have come from the 3 vectors that we just calculated. 4i hat is the vector that lands right on the x-axis. So this is the vector that comes from t equals 0, and we can see the point on the ellipse right here. 3j hat is the vector that lands perfectly on the y-axis. This happened at pi over 2, and we can see the point on the curve right here. And then lastly, our last vector comes from negative 2 in the x direction and positive 3 root 3 over 2 in the y direction. We can see that point here, and we know that this came from evaluating the function at 2 pi over 3. So we can see that as t is increasing, the vector function has a direction, and it's being evaluated in this direction. Now, often when we graph vector functions, we do not keep the vectors on there. We just graph the set of points. So the vectors are what's helping us generate the curve, but they're not an essential part to the graph of the function. What we do like to include more than just the points, though. We have all the points, which is the orange curve that you see on the screen. We do like to include at least one arrow to say which direction the function it has. So the increased value of t generates the curve in that direction. This is important because let's say I had a very similar function. Maybe I won't call it r, maybe I'll call it w of t. And maybe it looks like 4 cosine negative t plus 3 sine negative t. This curve will look exactly like the orange curve. However, the direction is in the opposite direction because I flipped t backwards. So it is important to take into account the direction of the vector function. There is another part to this question which says, do any of the composite functions have domain restrictions? Meaning, is there a value of t that would take this vector function and cause either one of those components to be undefined? And the answer is no, because sine and cosine are continuous everywhere. Let's take a look at this next vector function. We have 3 tan t I hat plus 4 secant t j hat plus 5t k hat. And we want to evaluate this function at those same t values. T equals 0, t equals pi over 2, and t equals 2 pi over 3. Now I want to encourage you to pause the video here, try to evaluate this function on your own. Even if you are using a calculator, go ahead and give that a shot and then check your answers with mine. Evaluating the function at t equals 0, I get a 0 in the I hat component, 4 in the j hat component, 0 in the k hat component. Evaluating the function at pi over 2, when I try to plug pi over 2 into tangent, I get a domain error. And that's because tangent, if we remember, is sine over cosine. Cosine equals 0 at different multiples of pi over 2. So if we allow t to be an odd multiple of pi over 2, we will have an undefined component function. And even if the other two components are just fine, one of them is not, and that's enough to break the entire function. So our vector function does have a domain restriction. T cannot be an odd multiple of pi over 2. It can be even multiples of pi over 2. 2 times pi over 2 is pi, and that's not a problem. But pi over 2, 3 pi over 2, 5 pi over 2, all of those cause a 0 in the denominator, which means undefined. All right, moving on, we have t at 2 pi over 3. The vector function r gives me a negative 3 root 3 I hat minus 8 j hat plus 10 pi over 3 k hat. And if we tried to graph this vector function, we would see that we have a bunch of disjoint curves in 3 space, much like what we see when we graph the tangent graph. Remember that tangent has a bunch of vertical asymptotes and then a cute little squiggle in between them. And every period is separated by these vertical asymptotes. And we see that in our vector function as well. Now we could restrict t so that it's between any two of the domain restrictions. So maybe we restrict t to be between negative pi over 2 and pi over 2, then we would just get one of those curves. And we could try to match up the vectors that we found, like r at t equals 0. It's really hard to see in this picture, but right here, the graph does cross the y-axis, so that would be the vector for j hat. And then we can match the next vector up. 2 pi over 3 gave us a negative x, a negative y, and a positive z, which means it's got to be pointing somewhere back here. Maybe that's not perfect, but that's enough for us to be able to see the direction that the vector function is working in. T equals 0 is here. T equals 2 pi over 3 is here, so we know that this vector function travels in this direction. Now we just graphed the vector function for cosine t I hat plus 3 sine t j hat, and we saw that it generated this orange ellipse. Something that's really neat about vector-valued functions is that we can reparameterize them, meaning we can change the parameter without changing the way that the graph looks. So notice that the second vector function that I have here, it's different than the first because it has t cubed. In fact, I could change this completely to a different letter, like s, so that it's not even t anymore, it's s cubed. And the graph would look exactly like it did before. So this is something that we will use in the future. The fact that we can change the parameter within a vector function without changing the shape of the curve. The last thing we have to talk about in this section is limits. Now, if you think back to Calc 1, the first concept that you should have discussed is limits, and that's because limits are the foundation for differential calculus. We need limits so that we can talk about the limit definition of a derivative. So we're going to follow that same process here. If we want to take the limit of a vector function, like r, we need to notice that vector functions produce vectors. So the limit will also be equal to a vector, like the vector L. And we'll use the same notation that we used in Calc 1, the limit where t approaches a of the function r is equal to the vector L. So notice the limit of a vector is equal to a vector. And this limit is true so long as the distance between these vectors, or the magnitude between the vector difference r minus L, needs to get infinitely small as t, the parameter, approaches some value a. So this is saying that when I let the parameter get close to a, that the vectors r and L get infinitely close, so close that the distance between them is 0. Now remember that a vector function is made up of 3 component functions. So when we take the limit of a single vector function, we're really breaking it up into 3 separate limits, one for each component function. And this is great news because it's just like Calc 1. Once we take the vector function and break it open and apply the limit to each scalar component function, this is a Calc 1 problem, but threefold, potentially. So let's try a couple of limit problems. I want to take the limit of the vector function that we see here, t squared minus 3t plus 4 in the I hat direction, 4t plus 3 in the j hat direction. And it might be worth identifying the component functions. So the f of t component, the f of t component function is multiplied by the standard unit vector I, and the g of t component function is multiplied by the standard unit vector j. So we need to start this off by separating our limits into limits of each component function. And I'm going to put brackets around that limit with the standard unit vector multiplied outside so that it really highlights the fact that we are taking the limit of component functions, not just scalar functions. And as long as we don't have any indeterminate forms, remember those pesky 0 divided by 0 indeterminate forms that were super frustrating in Calc 1? As long as we don't have that, then we can just plug and chug. Direct substitution. Replace t with 3 and simplify. Now I do like to admit that I like parentheses a lot, but I want to take a moment to remind you that these parentheses that I'm highlighting in white, those are not optional. We need to have those because they're grouping together the entire component function for the I hat standard unit vector. So if I dropped those parentheses, this would be incomplete. And then we take a second to, oh, my minus turned into a plus somehow. Take a second to simplify. We get 4 I hat plus 15 j hat. All right, let's try this next one. In this first example, I wrote out every single step, and maybe that's useful, maybe it's not. Maybe you get a little bit bogged down by writing limit over and over and over. If that's true, you can just think about in your mind that you're distributing this limit notation to each of the component functions. So if I look at the f component function and I apply the limit as t approaches 3 to that component function, it's going to look just like plugging 3 in to that component function. But don't forget that that all needs to be multiplied by the I hat vector. And then if I look at my second component function, like g, I can take my limit as t approaches 3 for that one. That would look like 3 squared plus 1 times j hat. And then lastly, our k component, limit as t approaches 3 for that component function, which we usually call h, would be 4 times 3 minus 3 times k hat. And then of course we simplify. Oh, I left a t in this first denominator. So in the I hat component function, we have a 2 on top, a 4 on bottom, or we have 1/2, which I don't need parentheses there. And the second one, we have 3 over 10 j hat. And then this last one, we have 12 minus 3, which would just be 9 k hat. So something that I want to again highlight is that if you're taking the limit of a vector function, the result should be a vector. And this is a little bit different than what we did in Calc 1. The limit in Calc 1 was always equal to a single number or a function of x, never a vector. It'll take a little getting used to, but I know you can do it. So the limit of a vector function will always be a vector. Now there's a couple of scenarios where that would be kind of strange. For example, what if each limit of the component functions was equal to 0? Well, the result is still not just 0. It would have to be the 0 vector. The 0 vector would have 0 in the I component, 0 in the j component, 0 in the k component, but it still has the structure of a vector. One last thing I want to talk about is the continuity of vector-valued functions. Now, vector-valued functions are made up of scalar functions. Each component function is a scalar function, which means everything that we know about scalar functions from Calc 1, it gets to carry over to Calc 3, which is awesome. In Calc 1 and previous courses, you probably learned that a function is continuous if you can draw it without picking up your pencil. Polynomials are always continuous. Rational functions are mostly continuous except for points where the denominator is 0. Those three things are still true. But the formal definition of continuity has 3 parts to it. It says, 1, the function has to exist at the point t equals a. So we start by checking continuity at each individual point on the function's domain. So 1, it has to exist. 2, the two-sided limit has to exist. And then 3, the first 2 parts have to agree with each other. So part 3 says not only does the function have to exist, not only does the two-sided limit have to exist, but they have to be equal to each other. The shortcut is that if each of the component functions is continuous, then so is the entire vector function. So there's not really a new trick here to determining if a vector function is continuous. It's old material, but remember it's taking a vector function, a single vector function that might be made up of 3 components. So this is like a 3-fold problem, where in Calc 1 you looked at a single function and you determined continuity once. For Calc 3, you look at a single vector function. You would have to determine continuity for each of the component functions.